Welcome to the meeting, REU, REU meeting. This week and next week will be a workshop for the computational modeling of quantum materials and disorder. This week, we will have Hanna to talk about the theory of random disorder material, and I will give a short tutorial afterwards. Next week, Jan and Marcus will discuss a package for calculating real materials. So if you're ready, Hanna, you can go.
Yes, thank you, Kamin, for a nice introduction, and welcome everyone. It's so good to see you all here, and especially students. You are very welcome to participate in this workshop, and I hope you will find it useful, not just today, but even for your probably future careers. And before I go on, I would like to thank Dr. Juana Moreno at LSU for kindly hosting this workshop at LSU. So thank you so much. And also, we all would like to thank you, our funding agency, NSF, for supporting our collaboration and research projects under multiple NSF grants in this collaboration. Okay, so this is the agenda or the overview of the two-day workshop. So computational modeling on quantum materials with disorder. We put a lot of key words in the title. So I will try to decipher what the title means for you. So that defines the structure of this workshop. So on today, day one, we will have an overview. We'll start with the overview, what quantum materials are and what quantum research is. I hope you will get some ideas where even probably to pursue your PhD on. And we will have some overview of various computational approaches used to study quantum materials, and especially the focus will be on the materials with disorder. And after the 30 minutes, I hope, presentation, we will have a hands-on experience number one, which will be run by Kamin, on how to use some exact normalization tool and how to use Green's function method to study some disordered models. Next week, we will have our day two, and this will be run by Dr. Jan Wan and Dr. Marcus Eisenberg from Oak Ridge National Lab and Carnegie Mellon University. And we will focus on ab initio or first principle studies of quantum materials. So they will give us some introduction on different methods used to be used, ab initio methods used to study quantum materials, and in particular multiple scattering theory and numerical framework MUST that we are all involved in developing. And you will have an opportunity to try your hands in running MUST and how to use MUST numerical framework to study disordered alloys. Within a couple of days, the workshop slides and presentation material will be available on our GitHub MUST web page, and also this videos of the workshop presentation will be recorded and posted on our YouTube channel. If you can follow the links, these two links, you will be able to find the information and go through this later on your own if you wish to. Okay, so let me just start with a general introduction, because I know that students are from very diverse background. Only several of you are physicists, so I thought that would be useful for you to get a more broader picture of the field. So as we all well know, that materials have been always as a driving force for the human civilization and development, right? Starting from the Stone Age, going through Iron Age, and more recently through Industrial or Informative Age, right? There has been a lot of breakthrough in the human civilization due to the different materials developed, right? Materials affect the way we live, the way we build our houses, the way the cars, the type of the cars we drive, what we eat, how we live, what we wear, how we communicate, how we work, and etc. Right? It affects all areas of our life. And now we live we are in the midst of we live in the quantum age, or in particular, we are in the midst of the second quantum revolution. You might wonder, when was the first quantum revolution happening? So this is related to the silicon or informative age from 19th century, from 20th century, right? So the first quantum revolution started with the development of the field of physics, which we called quantum mechanics. This is relatively new field of physics and only was developed in the beginning of 20th century, but it has a huge impact on the way we live now, right? Because quantum mechanics led to the development of semiconductors, and that led to the development of transistors, then of integrated circuit, and then we have this computer technology developed, which changed completely the way we study, the way we live in modern world, and we work in the modern world, right? And I think approximately from 2015, now we entered this age of the second quantum revolution, where, unlike in first quantum revolution, the same is that first quantum revolution gave us the rules that govern a new physics reality, and during the second revolution, we're going to use these rules to develop new technology, quantum-based technologies. Oh, I see something in the chat, so let me double check. Okay, thank you for putting the links, appreciate this. Yes, please follow the links to find more information. So if you read the news, I think you just Google quantum stuff and you will see that our future does look quantum. Okay, and this is based on the fact that quantum-based application will drive technological progress of 21st century, the same way as silicon-based technology drove the development during the last century and keep doing that, right? Quantum-based technology will lead to the changes in industries and science, including development of quantum internet, quantum simulators, quantum sensors, quantum atomic clocks, even quantum computers, right? Much more powerful things that we are dealing with now. As a result of the breadth of opportunities offered by quantum technologies and industry, there is now a global competition all over across the world. Government all over across the world are investing a lot in quantum science and technologies. And I give you this a picture just to give a flavor, right? I just give you a picture of how much money is invested in quantum technologies in all across the globe, okay? And different governments all across the globe also launched multiple quantum initiatives, including United States. In 2018, United States President and Senate accepted the National Quantum Initiative Act, defining quantum research as a national security issue. So if you follow this quantum.gov link, you can find multiple reports and up-to-date information of the progress in United States in this arena. Also, United States research, main research agencies like National Science Foundation, Department of Energy, Department of Defense, they are all underlying identifying quantum material research as a prime research, among the prime research direction in the field, and are heavily invested in it. And also, this is very interesting time because in addition to fundamental research, industry is also heavily invested in quantum material research and technological application. So big players like IBM, Intel, Google, Microsoft, they are all heavily invested in quantum information and quantum material research. So if you are a student, and many of you are students, I think this is a golden time. It's exciting time to be a student and a very excited time to go to do a PhD in this area. Okay, and since we are at this point at LSU, I would encourage you to take advantage of the existing resources at LSU. I mentioned there are different quantum initiatives launched across United States, and I look at your background, so I know that you're coming from various states, so you can first homework could be, you can go and search what quantum initiative or quantum centers are launched at your home state. And if, since we are at LSU, so we can take advantage of existing quantum Louisiana Quantum Initiative. If you Google this, and it gets you to this website, and you will see that there are many groups and many directions are explored through this quantum initiative. And one of them is to study quantum materials. And if you follow that link, you will see different researchers involved in this part of the initiative. Some of them you might recognize because they can be, they probably are your REU core mentors. But what I want to emphasize here is that if you look at the research area of these people involved in quantum material initiative, you will see that you have experts from a very diverse fields like physics, chemistry, material research, electrical and computer engineering, chemical engineering, biomedical engineering, right? So there are room for everybody, and it's just because that nowadays this quantum materials is like a unifying concept across very diverse field of science and engineering, right? Physics, chemistry, and engineering, computer science. And I know this is relevant to you because you are also, many of you are not physics majors, some of you are chemists, many of you are engineers, and many of you are computer scientists. So this is very good. So you are in the right place and in the right time. So you don't have to be a physicist to get involved in quantum material research. There are plenty of opportunities for all of us. Okay, so now let me give you some kind of a textbook example of quantum materials. I think one of the canonical examples of quantum materials, it's probably fair to say, are superconductors. Okay, so what are superconductors, right? So you know, when we run electricity, conductors, right? So electricity, like we have electric cables in our homes and everywhere, right? That runs the electricity. So we know in this conventional or normal conventional conductors, cables that we use to power up our homes. We use like normal metals, and in these materials, the resistivity, right, as we increase temperature, is going to increase with temperature. So basically what I'm trying to say here is that in normal materials, which are not superconducting, when we run the current through the material, we have dissipation of current, we lose the current due to the heat. Because inside electricity is a flow of electrons, and when they run through the cables, they get scattered of impurities, phonons, and other things, and we lose this energy, electric energy, due to the heat. Okay, and the higher the temperature, the larger will be the resistivity, the more heat we will get when running current through the material. However, there are these very special materials, quantum materials, which we call superconducting. So they are conducting electricity, but it turns out that these materials, when cooled down to some very low temperature and below some critical temperature Tc, these materials can run the current with resistivity going to zero. You see, there is no resistivity here, so there is zero resistivity. So they become superconducting, right? So they can run the current or electricity without any loss due to the heat, right? And this is fantastic, right? Because we live like in modern world, right? When everybody wants to have electricity at home, hot water, air conditioning, and other amenities, right? We are running into some energy issues, right? Energy source issues. So having conductors that can run electricity without any loss will be fantastic for us, right? But then there is a problem here, a little bit of a problem, right? So superconductors have been developed in 1911, but the temperature at which they become this superconducting, right, that can run the electricity without any loss of heat is too low. It's like absolute zero, right? Well, we cannot apply them to the everyday application, right? So over the last century, right, and several centuries, there has been a lot of studies in developing and searching and developing superconducting materials that we can apply in a room temperature. So the research was focused on how can we find or design the materials that would have this critical temperature Tc, at which we will have these fantastic properties, at room temperature, close to room temperature, so we can employ this material in real life. So breakthrough have came in 1987 with the discovery of so-called high temperature superconductors, where the critical temperature is around liquid nitrogen. Well, it's not zero, it's still cold, okay? It's still cold. It's not zero, but it's still cold, okay? And recently, like I think last year, there have been room temperature superconductors discovered with based on the hydrogen, but those materials have superconducting properties at extremely large pressure. Okay, so there is also limitation to their application in real life. But anyways, researchers are working on this type of materials and working very hard. How can we push this critical temperature to such extent that we can apply this material in real life? Since so superconductors are like canonical example of quantum materials discovered, but 21st century has led to the development and discoveries of numerous quantum materials. Okay, so and if you look through LSU webpage and this website that I told you about, you will see that scientists at LSU physics department are doing research in multiple quantum materials, including topological materials. So in these materials, topology matters. So on the surface, they behave like a conductor, but when you dip inside on the bulk, they behave like insulators, non-conductor, right? So topology matters. You will find that some researchers do research on ultra cold atoms. Some are doing research on graphene system, right? Which also recently there has been a Nobel Prize. And also there are multiple groups that are working on two-dimensional material. So where dimensionality and confinement of electrons changes the properties of the system. But anyway, there are many classes of quantum material discovered over the 21st century. One of the unifying theme of this material is that emergent behavior. You put many electrons together, you squeeze them as a dimensionality, you change the topology, or do something else, and the physics, which is new physics and exotic physics, emerges with exotic states of matter, emerges. And what we want to do, we want to utilize these exotic states of matter and in novel 21st century technologies, right? And so indeed, quantum materials are most technologically promising materials of our future. There are numerous potential application of these materials. For example, superconductors that I mentioned before can be explored, have been already explored for energy transmission. They're used in MRIs, in medicine. They're used to create a very strong magnetic field in accelerators to study high energy physics, right? We can use these modern quantum materials and manipulate their property to construct more powerful electronics, build quantum supercomputers, and also to design materials with the properties, with the functional properties, with different properties that we can use in multiple areas of our life. Okay, so now let me go a little bit deeper into a little bit of physics of this. So when we talk about quantum physics, this is actually, like as I put it, this title from the book, this is a physics of small things making a big impact in our life. So when we talk about quantum physics, this is a quantum world. We're actually dealing on a very small scales, on the level of nanoscales or even smaller. So for example, if you look at a matter, in a physicist, when they look at a matter, for example, they see not a box, they see a crystal. When you have ions sitting in these dots represent the ions, and electrons are moving around these ions. So this is like a nanometer level. And ions are charged atoms, right? Atoms are made of electrons, and you have nucleus, which are formed with another elementary particles, right? So we are talking on the level of nanoscale, atomic at subatomic level. That would govern the quantum world. And in such extremely small world, nano and small and atomic at subatomic level, the physics of microscopic physics, like what we call Newtonian physics, right? The physics which governs everyday life, doesn't apply. Okay, then we have this very strange behavior, and we call it, when we have new rules of physics applies, and we call it quantum mechanics rules. And in this world, what we used to call like particles, for example, electrons, they are particles, right? So when we call about particles, like we can consider ourselves as a particle, right? We can know where our location is, where our position is. I can call you and tell you where, you can tell me exactly where you are, right? So particle has the possibility to be localized in some position, X, you can have some velocity, and you can tell me, and we can predict your position velocity at any time, okay, based on the Newton mechanical rule. But in quantum mechanics, quantum particles, they don't have this kind of particles. They are a mixture. They are a mixture between particles, which can be localized in the space, and a mixture of the waves that can be spread out along the space. Okay, so for quantum mechanics, electrons are particle and waves at the same time. The same is with light. Light is a wave, but at the same time it has properties like particle properties, like a quanta of light are called photons. Okay, so we have this particle wave duality, and in quantum mechanics then that has a consequences, because in quantum mechanics we are not talking about position of particles and momentum, we're talking about probability of finding the particle in some space and with some momentum and at some time, and that probability we describe as so-called wave function that we are trying to solve when we're studying quantum mechanical problems. So when we're talking about quantum mechanics, we're trying to solve one of the most important fundamental equation of quantum mechanics. This is Schrödinger equation, which is H is a Hamiltonian, which describes the energy present in the system. Phi is a wave function, and E is the eigenvalues, eigenenergies of your Hamiltonian. Okay, once you know wave function or energy, you can calculate everything. Okay, but anyway, so what do we know about quantum mechanics from quantum chemistry or quantum physics? So when you look at the atomic level, so we know that electrons in atoms are, so things become, first of all, things become quantized. Okay, they're not continuous, things become quantized. And electrons in atoms are seated on energy levels, these quantized energy levels. And when you consider, like a physicist, you look at the crystal, right? You have many atoms in the crystals, you bring them together, each of them brings their own individual energy levels, and then these energy levels in a crystal would form energy bands. Okay, and when we describe materials in physics, we can we look at the energy bands. So we can look, we know that, for example, they form like valence band. All of valence band is fully occupied with electrons. Then there is a conduction bands, and based on the structure of these energy bands, we can distinguish between either the materials as a metal, semiconductor, or insulator. Okay, for insulators, there is a large gap between valence band and conduction band. For semiconductors, the gap is smaller, so electrons can be thermally excited and go to conduction band and run the electricity. And for metals, there is no gap in the density, in the energy spectrum. Okay, and if you are a computational physicist, and one can calculate such energy spectrum, like energy versus momentum, and calculate the energy of different electrons in your crystal. You can sum over this momentum and so calculate such quantity like density of state, and use, like shown here, for example, and here. And you can use this density of states behavior to distinguish between a conductor and insulator. So again, for metals, there will be no gap in the density of states, and for insulators there will be a gap in the density of states. And we will have examples of how to run like this energy spectral calculation of density of states later on in our hands-on tutorials. Okay, so how do we do computational research of quantum materials? So, well, when we have a quantum material, right, we want to study its properties, right? How do we study its properties, right? We want to see how this material is responding to different external parameters, or different external perturbation, or different research knobs. What do I mean by this? For example, we take a material and want to study what happened to the properties of the material if you change the temperature, right? You heat it up, what happens to it? Will exist superconducting states that I discussed before? Is it going to stay, or is it going to be limited to some temperature and go away at high temperatures, right? Then we can apply pressure and see what happened to the materials. Will it stay? Will you have a new properties emerging? Will the existing property exist, or something like that, right? So temperature, pressure, are powerful things that one can tune to study the properties of the things. Doping, when you put when you have a sample and you put in atoms of other kind into the sample, that's what we call doping, is another powerful tool to change the properties of the material. And this is like, for example, here is a temperature doping phase diagram of high temperature superconductors, where you can see that. So these different colors represent different states of matter, okay? You can have antiferromagnet, so some quantum magnet, okay? You can have strange metal, and what you can see as you dope the material, right? You introduce different atoms into the sample, the superconductivity emerges in this region, okay? So superconductivity can be driven by doping, for example, induced by doping in this material. And then what happens, you heat this up, things are going away, right? Superconductivity gets destroyed and you get into some another phase which you call strange metal. So all these different phases of matter have different properties and they can find different application in technologies, okay? The focus of our study is to use disorder as a turning knob to manipulate the properties of the materials, okay? Why disorder? Well, let's use the Stephen Hawking words, right? One of the basic rules of the universe is that nothing is perfect, okay? Materials are not perfect too. So perfection simply doesn't exist. And our research, the research of our collaboration, is the goal of that research is to use disorder as a tuning knob to manipulate the properties of quantum materials. And we want to do it in controllable way. So first, we want to understand what introducing disorder brings into the system. What does the disorder induce effects in the soil, right? We want to understand this. Then once we understand this, we would like to understand how we can control this effect into the system, the disorder effect in the system. Once we have that understanding in control, we can possibly predict new materials based on changing disorder, amount of disorder in the system. Okay, so what do I mean by disorder? So any imperfection or deviation of the system from perfect sample is, by this we mean a disorder, right? Impurities of different kinds and defects. Like, for example, this is a crystal, like in blue color, and you can have like atoms are sitting like in a periodic arrangement and the right spots, but you can have some imperfections or some defects. For example, you can have some interstitial atom, which is not in the right position, just squeeze a little bit off from the proper position. Or you can have some absence of atoms, which we call vacancy, okay? Or you can introduce some impurity or some substitutional impurity atom into the system. You take another atom and you put it in. That's also, if we call it disorder. Okay, so how does disorder appear in the system? You can do it intentionally or unintentionally. So unintentionally, it emerges when you grow or synthesize a sample, okay? Something can happen and these vacancies and impurities can emerge. Or you can do it intentionally, okay, by introducing different atoms, substitutional atoms into your sample and changing the properties of the materials like we can do in superconductors. Okay, so, and of course, as you can probably imagine, the disorder can have multiple effects on the properties of the materials. But the focus of today's workshop and one of the focus of our research direction is to use disorder as a tool to drive the phase transition. What do I mean by this? Phase transition is transforming system from one state of matter to another. And you might think it sounds complicated, but you are all very well familiar with this phase transition in everyday life, okay? So one of the examples is that you are familiar with is a solid liquid phase transition, right? It's hot outside today, you take ice, you put it into your tea or coffee, right? It melts. So we have a phase transition from a solid to liquid. And the thing that is changing this, driving this transition is a temperature knob, right? Because you're changing the temperature, you melt the ice, okay? Here, we are trying to talk about similar phase transition, well, similar to some extent, right? That we can change the knob in particular disorder, and we can try the phase transition from a metal, when you have electricity in your circle, like a conductor, to an insulator. It turns out that one can do this by putting disorder into the sample. You can change the conducting properties of the material and drive the metal insulated transition. Okay, This phenomenon of disorder-driven metal-insulated transition is a well-known phenomenon in physics. Phil Anderson it's called Anderson localization, and it was discovered by Phil Anderson, who was the first one to point out that electrons, right? I mentioned that electrons can behave like a wave when they are moving not a periodic crystal, but they are moving in disordered crystal or disordered sample. Instead of being like a block wave which propagates all across the sample, electron can behave like a localized wave, like shown here. And then instead of propagating of the sample, they will form this localized space within certain region of the sample. Okay, they will have this envelope-like structure of the wave function, and this kind of behavior we refer like localized states. When they are localized, so they are not moving across the sample, they cannot carry the current, and they become insulated. Okay, so disorder can drive metal insulated transition. We call it Anderson localization, and it turns out that such Anderson localization of electrons due to disorder can be actually used to control and manipulate the functional properties of the materials. For example, we can use disorder and Anderson localization to destroy superconductors that I mentioned before. We can drive in new states of matter, like so-called topological Anderson insulating states, where on the surface they will be still conducting, and inside they will be Anderson localized, will be Anderson insulated. We can use disorder and Anderson localization to control the localization of electrons, to manipulate the properties of semiconductors and so-called photonic semiconductors, photovoltaic superconductors, which are used in solar cells and can be used to construct efficient solar cells. And of course, you can use Anderson localization to drive metal insulated transition. Okay, so there are multiple applications of disorder-driven Anderson localization in real materials. Okay, so that all sounds very great, but now how do we study this as a series? Okay, well, when studying quantum materials, whether disordered or non-disordered, there is a huge challenge. And the that challenge has been recognized a long time ago in the 20th centuries, and and I think the best way to one of the good ways to describe this is just to quote a famous physicist, right, Paul Dirac. Right. So he said that the fundamental laws of necessary for the mathematical treatment of large part of physics or chemistry are known. Basically, this is quantum mechanics, and write it as the most important equation of quantum mechanics, Schrodinger equation, right? However, we can write these equations, that's fine, but the problem comes that these equations that we have to solve, so the difficulty lies only in the fact that these laws lead to equations too complex to be solved. Right, because we have many electrons interacting or correlated electrons in the system, and when we want to solve the problem Schrodinger equation, because it's many, by many I mean 10 to the 23 particle Schrodinger equation, when we want to solve this equation, it's just impossible. Okay, so what is the solution? As pointed out by Paul Dirac, he said that it is very desirable that we construct approximate practical methods that we can apply to this quantum mechanical equation that would allow us to get some explanation and understand the main features of complex systems. Okay, so over the last several decades, numerous computational methods have been used as a practical approximate methods to solve Schrodinger equation. And computational methods can be divided in two groups. Okay, one, we call them ab initio or first principle methods. They are heavily used in physics, chemistry, material science, and engineering. And they are, and one of the most powerful tools that have been used to as ab initio method is a density functional theory. So in these methods, we take into account very accurately all electrons, all atoms, all ions, we've take into account accurately their position, all the interactions that are present in the system. Okay, so we don't use any empirical parameters. Okay, this is first principle calculations. On the other hand, we can do a different approach. We can take another route, and this is called model Hamiltonian approach. So instead of putting all the details into our equation, we say, no, this is too complex for us. Let's study a simple model or use some simple equation that can describe the phenomena we are after. So we are using the key players to construct the simple Hamiltonian, and our goal is not to describe the physics we are looking at quantitatively, but qualitatively, right? We are trying to explain the phenomena we are after. Instead of looking at complexity, we are looking at the simple and key players. Okay, and that's the reason we have this workshop divided in two days, okay, on two parts. On day one, we will show you how can we use model Hamiltonian approach to solve simple model for disordered system, and we will have time to give us hands-on experience on that. And on day two, we will take this route, and we will have Dr. Jan Van and Marcus Eisenberg to show us how we can use ab initio approaches to study disordered system. Okay, so stay tuned. You will have experience in both ways how to do calculation in disordered materials. Oh, I'm running out of time. So let's go. Let me go to day one model Hamiltonian approach. So the simple model we're going to study is this Anderson model. And I told you we take the simplest models that we can take. So in disordered system, we have electrons moving on the lattice or hopping on the lattice. So the first term describes the hopping or jumping of electron from one side to another. And the second term describes the potential, random disorder potential, okay? And even solving this problem, it's not an easy task. And in today's hands-on activities, we will explore two ways of doing that. So to solve these numerical problems, one can use two ways. One way is to do direct numerical method. So you take your lattice and you do like exact generalization or supercell calculation. So you solve the Schrodinger equation and look for the wave function. Once you have eigenvalues and eigenfunction, you can calculate all properties you want. Okay. Another approach is to use so-called effective medium approach. So instead of solving the lattice, you are solving impurity embedded in some effective medium. And that effective medium is like mean field approximation, which contains the information about all the rest electrons, how they affect the electron on that impurity. Direct numerical methods are often wave function-based approach, and effective medium methods are Green's function-based approach. And you will play today how to calculate all these quantities today. Green's function-based approach have one advantage that we can calculate quantities which can be directly related to experiments. For example, you can calculate density of states or spectra or conductivity or resistivity and compare with experimental finding. Okay, and this is we will have a hands-on experience on this, doing exact generalization and Green's function method on a simple model, 1D Anderson model. Okay, and I will conclude this presentation just to highlight that if you want to learn a little bit more about different methods used to study disordered quantum materials, I would like you to invite you to our GitHub page and our YouTube page of our MUST collaboration. This is multiple scattering theory computational framework for disordered material. This is multi-institutional international collaboration and a self-funded 3-year project where I developed different computational technique ab initio and quantum embedding methods. And the codes and numerical framework is freely available through our GitHub. So please use this link to download that software. And if we also develop numerous lectures to study quantum materials, that I would like to welcome you to watch this YouTube video, subscribe, and explore what interesting opportunities you can have to perform research in this area. So if you're interested in doing research, please send us email or we can discuss more, and subscribe to YouTube and GitHub. Okay. So thank you, and I apologize. I went through the longest through the time. So I give the floor now to Kamin Tam.
Thank you, Hanna. First of all, do you guys have any questions to Hanna?
Yes, I had one question.
Go ahead.
So when you're building the actual Hamiltonian, and maybe this would be like a Schrodinger model, and you say it's a highly correlated material. So you assume that there's entanglement all throughout with all of those electrons in the entire Fermi band.
Right. So so you can do like quantum Monte Carlo method, for example, to study this correlations effect.
Okay, so y'all call that correlations.
Yeah,
I say information. So
correlations means that they are not moving independently. That's what I mean by correlations effect.
so that'd be their propagation through the crystal.
So like motion of one electron really depends on the motion of another electron, okay? And that like independent motion have this result in this many body effect that we see in quantum materials.
Huh. And would you consider that like I'm familiar with correlation as like an entanglement of states. Is that?
Yeah, you can say that way too.
Interesting. Okay. And then if you go to DFT, is that just like a local density matrix for each atom that then you're
Yeah, well,
over?
that's a very good question. In DFT method is mostly applied to weakly correlated material where we have like independent electron motion, okay? So, but if you want to do really study correlation, so you can use this embedding method like DMFT or quantum Monte Carlo on a lattice, then you can really take this correlation effect properly. But you're right, for DFT is independent electron motion of weakly interacting systems.
I see.
Very good question.
Thank you.
Mm-hmm.
Yeah, so DFT captures some correlation, but the popular approximation to the density functional are local. So they only depend on local quantities of the density, like the value of the density, the gradient of the density, and so. And that is shown to not be able to capture the full correlation, which would require an extended functional.
I see. But even then, are you assuming that you have some kind of, do they call it like a Fermi band or something where it's an approximate orbital or something over the entire lattice that it's all occupying based on some temperature?
Fermi band, I'm not sure what Fermi band. We know energy.
Yeah, I'm trying to think about how I'm thinking about it. Like if all these electrons are in some energy level, like you said, that they're averaged over some density of state, that's defined by the temperature and some other, but some system mechanics and stuff like that.
Density functional theory on its own is a theory of the ground state.
Okay. Okay.
I think you're talking about multiple band cutting the Fermi surface.
I'm not too familiar now. I'm just thinking out loud, sorry. Yeah, that makes sense. Thank you.
Yeah, but like the popular version of DFT is normally derived by like doing some minimization. So you're basically solving a zero temperature problem. And in this approach, you're typically mapping like an interacting problem over to a non-interacting problem, which is why you miss out on some of these correlations, if that makes sense.
Yeah, that makes sense.
Any other questions? If not, we will move to Dr. Kamintam to give us a hands-on activity.
Hi, Hannah. I have a question. This is Swarnava. So excellent talk, by the way. So my question is that, is there any real material which shows, like, can you give an example of a material which shows metal to insulator transition with disorder?
Semiconductor.
Semiconductors, yes, intermediate band semiconductors. I think recent experiments, 2019, 2020, superconductors, when you use disorder to destroy superconductivity, there is also metal insulated transition in that sense, but semiconductors, I would say yes.
Like silicon?
Phosphorus doped silicon is a classic example.
Silicon.
Gallium arsenide.
Silicon P, SiP, right? Gallium magnetic arsenide, yes.
Okay. And what was the like example of the room temperature superconductor that you said that was discovered in
hydrogen-based superconductors, but they require super huge pressure.
Okay.
Yeah, you can Google like room temperature superconductors. This was like, I think, October.
I see. Okay. Thank you. Thank you.
Mm-hmm.
Any more questions?